So let's look at the equilibrium constant of water. The water equilibrium constant, or equilibrium constant of water, the Kw value, is simply a Kc value for a very special reaction, right? So you might remember that a Kc value is something where we take the concentration of products and we divide it by the concentration of reactants, right? But you might know that as I've written it here, it is simply a device to help us to remember how to write it. Never ever in a test or exam will you write Kc equals products over reactants. You'll substitute in the correct things based on the reaction that you've got. Okay, right? So never write this, just use it to help you remember. Okay, so that's what a Kc value is, as we recall, right? So here we're going to be talking about a Kw value, which we said is a special Kc value. So what is it for? Well, it's for the reaction of water with water. Okay, so water can react with itself in order to actually form hydronium ions and hydroxide ions. Okay, and this is called the autoionization of water. So auto means by itself, right? And ionization, we know, is, you know, when we break these covalent bonds in order to form ions, and that's exactly what's happening here. So this reaction is called the autoionization of water, and if you've got pure water, that actually means that you will have in that pure water some hydronium ions and some hydroxide ions. Now, the Kw value for this reaction, and you might remember that Kc values only change with temperature, right? So that means if you have a given temperature, you will have a given Kw value or Kc value, right? So the Kw value of this reaction, which is the product of hydronium ion and hydroxide ion concentration, is equal to 1 times 10 to the negative 14, and this is true only at 25 degrees Celsius. Once we change the temperature, the Kw value actually changes as well, because we said Kc changes with temperature. Okay, so why on earth is this the equation? Well, these two things are in aqueous solution, so they do have concentration, so that's our product that goes at the top, but then these things here are pure liquids, right? And pure liquids, we know, do not have a concentration, so here our denominator is actually just 1, because the reactants, well, don't really have a concentration, they're pure liquids. Okay, so that's where this formula comes from. It is just a Kc expression. But let's then think about this number, 1 times 10 to the negative 14. And we might ask ourselves, well, is this a big number or is this a small number? And if you think about it, you might go, yeah, that's a pretty tiny number, very, very small, right? Which means that this equation here, products over reactants, if we get a very, very small number, then that is a bottom-heavy fraction, right? That means that we've got to have a really big denominator and a very small numerator in order to get such a small number. And what that means is that at equilibrium, we really don't have a lot of this, but we do have lots and lots and lots and lots of this. Okay, right? So pure water is mostly just pure water. The hydronium and the hydroxide ions are going to be of quite a low concentration. Okay, so what we can do now is just define the idea of neutral. Right, now you might be tempted to say that neutrality is a pH of 7, and you would be wrong, okay, because neutrality being a pH of 7 is actually only true at 25 degrees Celsius, right? So it's better to define neutrality by saying that it's when the hydronium ion concentration is equal to the hydroxide ion concentration, and it turns out that what that means is that at 25 degrees Celsius, yes, you will have a pH of 7 when it's neutral, but yeah, that only applies to 25 degrees Celsius. Okay, so neutrality, hydronium ion concentration is equal to the hydroxide ion concentration. Okay, so we've spoken about this Kw value of water, but the question is, why is it useful? Right. Now, what's super useful about it is that the Kw value does not change unless temperature changes, right? So it doesn't matter how much acid or base or whatever it is that you throw into the solution, the Kw has to remain constant. And what that means is that if you have the hydronium ion concentration, you can always use this to find the hydroxide ion concentration. Or if you have the hydroxide ion concentration, you can always use this in order to find the hydronium ion concentration, right? So let's say, for example, that we know in a particular solution, the hydronium ion concentration is, let's say, 1 times 10 to the negative 4 mole per decimeter cubed. Okay, so then the question is, what is the hydronium ion concentration provided that the temperature is 25 degrees Celsius? So for that, we can then just use Kw. So our hydronium ion concentration multiplied by our hydroxide ion concentration, which we now know is 1 times 10 to the negative 4, always has to be equal to this constant at 25 degrees Celsius. And so we can then go and calculate the hydronium ion concentration. So 1 times 10 to the negative 14 divided by this 1 times 10 to the negative 4, and then we get something like 1 times 10 to the negative 10. Okay. Okay, and that then would be the concentration of the hydronium ions. So this Kw value is super useful as a go-between. If you've got hydroxide ion concentration, you can find hydronium ion concentration and vice versa. Okay, and for example here, if we knew the hydroxide ion concentration was this, we could even go calculate pH, right? Because we might know that the pH is equal to the negative log of the concentration of the hydronium ions. Okay, so in this case here, it would be the negative log of that 1 times 10 to the negative 10. And that would give us a pH value of 10. Okay, so that pH value of 10 we know is in a basic range, but we're not surprised that this is basic because the hydronium ion concentration is substantially higher than the hydroxide ion concentration, sorry, the OH negative, is substantially higher than the hydronium ion concentration. So when, you know, the OH negative is more than the H3O plus in concentration, this is basic. Okay, that's the very definition of something being basic. And when something is acidic, we are going to have the opposite, right? You're going to have the hydroxide ion concentration less than the hydronium ion concentration. So more hydronium ions than hydroxide ions.